I think probably we can start right here. People can join me. Okay, so welcome to your NPTEL tutorial for your course on advanced quantum mechanics and with applications. So this is your week 1. So I hope you'll be able to access your lecture videos and rest of your like materials. I think that would be like accessible by all you. I mean, uh, I think there was also one assignment which is also out. So I hope you have gone through them, and I hope you try to solve them. So basically, the assignment is about your basic quantum mechanics. So since you know, like you are, yeah, since you are doing advanced quantum mechanics, I hope you all are familiar with at least some form of basic quantum mechanics. And uh, so you need to have at least some idea, like at least you should be aware of some basic postulates of quantum mechanics, some basic principles of quantum mechanics, and then it would be very easy to follow this course. So I hope, like, if some of you are not really very much aware of like the basic idea of quantum mechanics, I hope you go back to your quantum mechanics 1 course or the basic quantum mechanics course, and try to like understand that first, and then you can move on. So now, like, we will so this week, like, it's just like I think you have gone through the lecture videos, but the assignment is on the basic review of quantum mechanics, that like is basically uh, related mostly to your quantum mechanics 1 course. So like that can be a good way to refresh your uh, uh, basic laws that you have studied in quantum mechanics 1 course. So before starting, if you guys have any thing to say, like if you have some sort of doubt or something else, like some other comments that you want to have, so you can. Well, you people able to like access the week 1 lecture videos and all other materials, right? Well, can someone? Okay, thanks, Sanjay. Okay, so okay, like maybe we can start uh, moving on. So so it's basically your quantum mechanics review, that quantum mechanics 1 review that we'll be going through. Like we'll look into some problems uh, that is something like whose concepts are something very much quite familiar from your quantum mechanics 1 course. So like starting from the problem 1, so it is on infinite well potential. So uh, so again, infinite well potential you must have done in your quantum mechanics 1 course. So like so what is about like infinite well potential, like so that is a potential where you have a zero potential in a certain region of space, and other than that you have potential infinite all around it. So something. So like in infinite well potential uh, you have some reason like this 0 to L. So like this is one dimensional infinite well, so you can have like a general three dimensional infinite well as well, but we are dealing with a like a more special case of a infinite well, so where this uh, so this is where your potential is, and so this is where your one dimensional space is. So uh, you have uh, this this goes to infinity, so this potential basically goes to infinity uh, when you go beyond L, or when you uh, like uh, go beyond x equals to 0 to the other side of the space. So you have only v equal to 0 potential for x equals to 0 to x equals to L region. Otherwise, you have v equal to infinite potential for all other space that is surrounded by. So and so the if there is a particle trapped inside this potential well, so a quantum particle, that quantum particle will have a wave function, and I'm sure that wave function is something that we always define for a particle, that basically defines the state of the particle. So which you are already familiar with. I I hope so. And so um, for uh, the general form of wave function for a particle trapped in an infinite web would look something like this. So so this uh, so this is for the reason and otherwise. Okay, so now we can move on the problem. So the problem is basically telling us like a particle of mass m in an infinite square well potential, that is the potential which I just uh, talked to you about. So like is prepared in a state with a wave function this. So as I said, like in general, you can have a wave function like this for a infinite potential well, and here n is basically your integers that goes from 1 to 3 and so on. So so this is like for a uh, particle in any general nth excited state. So this is just like a particle trapped inside a infinite well, having energy state corresponding to some nth level. So your n decides the state of the particle. So like you have ground state, first excited state, second excited state. So for ground state, n is equals to 1, and for first excited state, n equals to 2, and so on. So that is your wave function of the particle uh, uh, trapped inside this potential well. And remember, this is just a single wave function. Like by what I mean is, this is not a like superposition state. So it's just a like this is your eigenstate. So like uh, the psi of x which I have written here, this basically represents your nth eigen wave function of your particle trapped in infinite well. So let me clear that here. This is your nth eigen wave function. So now here it is written in the question that you have a system, you have a infinite well system where your uh, okay, so your state is defined something like a sine cube pi x by L. Otherwise, it is zero if it is outside the boundary, that is x equals to zero and x equals to L. So, what is that like? If you would see, like, if you would try to write this, uh, so right. So you have psi of x, some which is given in your question is sine cube pi x by L. So, like, I hope you are familiar with this relation of sine 3 theta, where sine 3 theta is something written as 3 sine theta minus 4 sine cube theta. So, using that idea, like, we can express this a sine cube pi x by L uh, in the same way. So, that would be 3 times of, yeah, that would be 3 3a, so there is 4, 3a by 4 sine pi x by L minus a over 4 sine 3 pi x over L. So now you see, like, this is your wave function, which is exactly given in this question for the particle trapped inside the well. So now you see, like, you have two terms. So, like, earlier, as I was telling you, like, this wave function, like, used to denote only one single eigenstate of the particle. But now, here in this wave function, you can see you have basically two terms. So that means uh, you have two eigenstates at the same time. That means you have a linear superposition of two different eigenfunctions. So, and I hope you can also guess, like, which eigenfunctions are these two terms corresponds to. Like, the uh, from the first term, if you would see, the argument part of sine is pi x over L. So, as I said, the general form is uh, root 2 over L sine n pi x over L, where n is basically something that specifies your state of the wave function, like whether it would be ground state or first or second excited state. So, if you are writing n equals to 1, that would be your ground state, and if you're writing n equals to 2, that would be your first excited state. So, same way, like, from this wave function also you can tell, if you're writing n equals to 1, so that would be your ground state, and if you're writing n equals to 3, that would be your second excited state. So, but uh, we at the end we have to calculate the expectation value of energy of the particle. So we got the wave function. Now we have to calculate the energy. You have to calculate the expectation value of the energy. So the particle which is trapped inside the infinite well is in this state. The This is the state which the particle is residing inside the well. So it is in some linear superposition of two different eigenstates. And so if the particle is in this state, what would be its expectation energy? So that is the question finally which we have to compute. So for that, you know very well, like, if you want to calculate expectation value of energy, so you basically have to take uh, so this is your like the expectation value of energy. This is how you write expectation value. So that is your basic quantum mechanics definition for expectation value of any physical observable. So here the physical observable is Hamiltonian, because we need energy, we need expectation energy. So Like I hope you are also familiar with one other form of expectation value, like where it is given as something. Uh, let me tell you. Uh, if you have some psi, and if it is given in some form of C1 5 1 plus C2 5 2 plus so on till some nth eigenstate, then the expectation energy is something written as summation I C I, its magnitude, its uh, modular square multiplied with corresponding eigenvalues. So Ci are basically your uh, expansion coefficients of your wave functions. So, like uh, the wave function which is given to us is also something in the linear combination of two terms. So you see that like 3a by 4 and minus a by 4 are some are basically these constants which I am denoting by ci, and lambda I is basically your corresponding eigenvalues uh, or eigenvalues eigenvalues corresponding to each phi I. So you have eigenstate phi I, phi 1, phi 2, and so on till phi n. So these are the eigenstates, and their eigenvalues are basically denoted by lambda I. So I hope you are familiar with this relation, or is just even it's a bit simple to see. Like you can understand right from here. Let's say if you have psi something like this, and as I said, you like to compute expectation energy, we basically have to compute this thing. And so if you take uh, bra of psi and h acting on psi, so that means you have something uh, c1 star phi 1 plus c2 star phi 2 plus so on plus cn star phi phi n, and you have Hamiltonian, and that acts on C1 phi 1 plus C2 phi 2 plus, and that goes till phi n. So now from here you can see, like if I uh, like this phi and m are basically your eigenstates, so their inner product would give you something delta function, because if they are the same state, so that is basically your normalization, or basically the probability of your uh, that state. If they are different, so like those would be orthogonal states. So if you take the inner product of phi 1 and phi 2, that will give you 0. So like same way phi 2 and phi 3, phi 1 and phi 3, and so on. If you're taking the inner product of the same state, so that would just like if that wave function is normalized, so that would definitely give you 1. So so from here, like if you like operate this h on your right hand side of your uh, I mean, if you operate h on its right, so h will operate on each and every term of this wave function psi. So when h will operate on phi 1, so when h operates on some phi I state, so that will give some lambda I phi I, because these are eigenstates. So So from here, like you will see, like if you go on calculating this one, so here you will have C1 star phi 1 plus C2 star phi 2, Cn star phi n, and so C1 lambda 1 phi 1, C2 lambda 2 phi 2, and so on it will go. So from here you can see, like you use this two relation, just that would finally give you uh, something this. So tills C and so yeah, so that is what the uh, relation which I wrote earlier. So so this is just a like quick way to see like how this comes. I hope like most of you are already familiar with. If not, like this is the way like how you see how this relation comes. And so like coming back to the problem like which we were having right here, like we were given this psi x, and you can see this. You can call this some, each of this term is some phi 1 and phi 2. So so then like we can go on to calculate. So so from our original problem, your expectation value will be, uh, first term you have what, you have, so let me um, tell you that this corresponds to n equal to 1 eigenstate, and this corresponds to n equals to 3 eigenstate. So that means this is your second excited state, and n equals to 1 belongs to your ground state. So uh, yeah, so for uh, uh, yeah, like before going through, like there is like one more thing you need to make sure, like what would be your your value of a. So because this wave function which is given to you, it's not normalized. So since if it is not normalized, like you can calculate the value of a. So uh, like or maybe I can tell you at the end how to do that. So uh, from this definition, like you need to have Ci mod square. So we have two terms, C1 and C3. So, so your C1 is 3a by 4, and your and then you have, so for n equals to 3 you have this eigenstate. So let's say this is your uh, this is your C1, so this is your C2, and this is your C1, and your you have this is uh, and this is your phi 1 and phi 2. So so we have 3a, 3a by 4 square. Then the first wave function is your n equals to 1 eigenstate. So for n equals to 1 eigenstate, you know the eigenvalue. So that eigenvalue is given by pi square x bar square by 2m l square. So let me write this for you. So um, so the eigenvalue for each given, for each and I mean for every corresponding eigenstate will be n square pi square x bar square by 2m l square. So these are the eigenfunctions. So these are your eigenfunctions, and for each eigenfunction you have this respective eigenvalues. So here we have n equals to 1 eigenfunction and n equals to 3 eigenfunction. So for n equals to 1, it would be n equal to 1. So that is your pi square h bar square by 2 ml square. And then for the next term, you have a over 4, so that you square them up. So minus a over 4 square will be a square over 16. So a square over 16. Then you have 3 square pi square h bar square by 2 ml square. So uh, so so before like computing this, like as I told you, like you also need to determine what is a. So how can you do that? Like you just take the wave function which is given in the question. You take psi star, and you, I hope like you know how to calculate this normalization factors. So when you will compute this, so from here you will get like you compute like you from this equation, from this integral equation, you compute what is a. So because this psi star psi, when you integrate like over dx, so like so here you have limits 0 to L, because that is where your wave function is restricted. And uh, so so when you compute this integral, you will get some relation of a, so that will give you a for you. And when you get this a, put it right here in the exponential energy, and you will get it. So yeah, right. So then like I hope like this is clear for you. uh, Hello, Sanjeev. uh,
Yes, yes, sir. Yes, sir. Yes.
uh, Another question related to this infinite well potential. You have a particle in the infinite potential well, but this time you have your infinite potential well from x equals to minus L by 2 to x equals to L by 2. So earlier it was from x equals to 0 to L, but the length is still, it is L even this time. So and now your uh, infinite potential well has been prepared in this state, and the phi 1 and phi 3 are normalized ground state and a second excited state respectively. Calculate the following. So first you have to calculate the shortest time t after which the state will repeat itself. So basically what is asked in this question, right? Like you have a initial state, so that is this is your initial state of your uh, infinite well potential in which a particle has been restricted. So and if that system has been led through, and it will evolve through time. So after some time t, it will change into some other state. So and that evolution will basically guide that state to come back into its original form after some after some arbitrary time. So what I'm saying, if psi equal to t0 is your initial state, so when you will evolve it, so it will change into some other state. But there will be one time, or there can be many different time, like it can be t1 t2, or can be some uh, large time event, could be t8 t9. So after that time, that uh, that state will. So you have your initial state, which is half of phi 1 plus I root 3 by 2 phi 3. Let's say there exists a time t3, and after t3, you will get this same state. So that is what you need to take care of in this question. So that is what is been asked basically. So you need to calculate that time, so the shortest time. So you can say that like this psi t equals to 0, this exact same state, it can repeat itself after t equal to 2, then after t equal to 7, then after t equal to 11. So but the minimum time you have to calculate it. So minimum time is t equal to t equal to t2. So like we'll see like how this can be done, like. So uh, okay. So you have your state psi of x t equals to 0, phi 1 x plus I root 3 by 2 phi 3 of x. So now you have to evolve this. So uh, to evolve this, like let's say you want to, or like write this way. So at some t equal to t time. So yeah, at t equal to t prime, some t prime. So how can to evolve this? Like I hope you are familiar with this idea. You evolve using a evolution operator. So for this given wave function and the Hamiltonian, your Hamiltonian is basically your infinite well potential Hamiltonian, because that is what your system is. So you evolve with your infinite well potential Hamiltonian uh, of this form. So the your evolution operator would be something of this form. I over h bar h t. So this is your evolution operator, and that will be operated on your initial state. So that is x equal to x and t equals to 0. So that is what will be your evolution of your initial state, evolution of your given wave function. So so when you will do this, like so you have h t, uh, so you have half of x plus I root 3 by 2 phi 3 of x. So right, and again this phi 1 and phi 3, like these are your eigenstates. So this is phi 1 corresponds to your ground state, phi 3 basically is your second excited state. So uh, so let me tell you, if phi h t x on phi n. So write it right. So e I bar h t of x on phi n, then that will give you e n t phi n. Since phi n's are your eigenstates, so that is what the result you will get when you operate this evolution operator on each given eigenstate. So when you do that in this, uh, I mean in this expression, so uh, so you get something uh, like this e or yeah, minus I. So there would be a negative sign. So I missed all of them. Yeah. So E1 over H T. So there is a 1 over 2 factor, phi 1 you have plus I root 3 over 2 e minus I over h bar h3, sorry, the e3 t phi 3 x. So yeah, so this is your evolved uh, wave function, or that is the state of the wave function after t equal to t prime. So I'm calling this as t prime. So that means I have to evolve this with real t prime. Okay. So after uh, t prime, so you will have this wave function. So your state of the particle for which is trapped inside the infinite well will be of this form. So now, it's the uh, the main problem is which you have to identify here. What would be the minimum time so that this exact wave function will return back to the original form. So this uh, psi uh, x t equal to t prime will basically uh, be the same state as it was initially. So, uh, and I'm saying it that it would happen after t prime. So that is the t prime which I have to calculate. So, uh, so right here, like from the previous expression, like what I can do. So I have x equals to t equal to t prime. I can take like e raised to the power minus I e1 over h bar t prime. So I'm taking this a common factor. So like I can do that. Like maybe I should write it first. Uh, yeah, half phi 1 x. Yeah, I'm writing it as phi 1 to 3 by 2. So this will become yeah. So this will become e3 minus e1 or h bar t prime phi 3. So now here in this expression you can see I have a overall factor of exponential, an overall exponential factor. So this is just a phase. If you would see exponential of something iota, some parameter is always is going to be some phase, like that is like like you have encountered this in various places. So if you have a wave function like this, you given any wave function, like you, like for example, you have some wave function like let's say what uh, yeah, some wave function psi as something e to the power I k t phi. Then if you take like this wave function is after not your physical quantity. So what is physical at the end is when you take probabilities, when you take expectation energies. So when you take probabilities or expectation energies, like what you basically compute this kind of inner products. So when you compute this kind of inner products, you are left with this, and the exponential factor will go away because e to the power iota, when you take its complex conjugate, would be e to the power minus iota. So the product is itself is something will give you uh, just a factor of one. So uh, yeah, so uh, that is why like this phase factor becomes a redundant thing when you try to when you are basically dealing with probabilities or expectation values. So here also, like we can omit this phase factor, which will not be like affect our results at the end. Like I mean, that is one of the redundant factor which won't like make any impact when you uh, compute your uh, important quantities at the end. Like important quantities, I mean the physical observables that you will be calculating at the end. So the physical results that we want is probability or maybe some expectation value, some other physical observable could be energy or momentum, something. So so yeah, right here, like I can take this overall phase factor, and so I can say psi x t equal to t prime is basically this. So like we can ignore this factor. So now you can see you have your uh, yeah, Alex Sanjeev has sorry, yeah, uh,
Sir, how it can be ignored, sir?
yeah, KT 5. So, what I'm saying, like what we want at the end is like probabilities or something like expectation value of energy, like the expectation value of energy which we calculated just in the previous question. So, let's say I want to know what is the probability. So, to compute probability, I will compute something this. I will compute the inner product of this quantity. Or if I want some expectation energy, I will compute this. So in both this you will find like if I am what is this quantity, this bra side and with get side. So bra side is basically phi minus I k t, and your get size e I k t phi. So that is basically phi phi. So here also you will get something phi h phi. Now, let me tell you, like if I have psi without this factor e to the power I k t, if I have something just phi, then what is psi? Like it is basically phi and phi, and so on the expectation value of energy. So you see, like both these results like are basically same. So when you have the overall phase factor with you or not, like uh, it will not matter at the end, because you have your results, you have your physical results unchanged. uh, like this overall phase factor, this e to the power I k t won't affect your final result for your physical quantities. That
Okay, sir. Thank you, sir.
so here also, like we have this factor, overall factor. So inside it we have another phase, but that is not, you are going to ignore it. I mean that is very important, but you like uh, you will see that this entire some wave function, some you can say something phi, this entire thing. So something phi. So you have overall phase vector of e to the power minus ei. EI by h bar. So I hope is this clear for you?
Yes, sir.
Okay. So yeah. Okay. So yeah. We have this form of wave function after t equal to t prime. So now what we want basically, I want this thing to be this psi at t prime is base should be equal to psi t equal to 0. So like if you would compare this psi which is at t equal to t prime and t equal to 0. So at t equal to 0 was this. So you will see that the first term is exactly as it is, half of phi 1. So here also you have half of phi 1. But the second term you have I root 3 by 2 phi 3 initially. Now you have that same I root 3 by 2 phi 3 but with this exponential factor. So if we want psi t prime to be equal to psi t equal to 0, then we want to make this exponential factor going to 1. Only then you can, uh, that would imply psi x t equal to t prime is basically equal to psi x t equal to 0. So only then you can say when this exponential factor will go to 1, then you can say that your psi at t prime is basically equal to psi at t 0. So, so we basically have to make E3 minus E1 over H bar. So this is T prime is equals to 1. So, uh, so if this is equal to 1, uh, or otherwise I can say this thing is basically equal to minus I to m pi. Like I hope you know this identity. So whenever you have something exponential, these are basically Euler functions, exponential of uh, minus I to n pi. That is uh, that is basically 1. So you can just check it like from the Euler's identity, like cos of 2 m pi plus iota sine 2 m pi. So sine of 2 m pi will be 0. So and cos of 2 m pi is, of course, that will be 1. And yeah, cos of n pi, and if m is odd, then that would be minus 1. So in that case, I would have written e to the power like minus I 2m plus 1 pi is minus 1. But we want 1 right here because uh, we when we make this exponential factor to be 1, then it will basically uh, give the initial state. So yeah, so we have to equate this exponential with this. So that means we have e3 minus e1 over h bar d prime equal to 2m pi. So now d prime, uh, yeah, d prime is basically 2m pi h bar over e3 minus e1. So now uh, here m can be, so here m is basically 0, 1, 2, 3, so on. So for m equals to 0, like, so that means we have 0, and for m equals to 1 you have 2 pi h bar over e3 minus e1. So on it will go 4 pi h bar e3 minus e1. Yeah. So these are the times, these are the possible values of t primes, in which your psi at t prime will basically equal to psi at t equal to 0. So you have all these different times like 0 to pi h bar over e3 minus e1 and 4 pi h bar over e3 minus e1, and so on. It will go to like 6 pi h bar e3 minus e1 and so on. It will go on. So there are many times after which at that, I mean, in at those times the wave function will basically be equal to the wave function. It will be equal to the initial wave function. So, but here it is asked what is the minimum time. Minimum time, you will see, like you will say that it would be zero, but zero is basically where the state has started. So zero is what is your psi uh, x t prime is zero is basically what is given in your question. But psi x t prime equal to this psi x t prime equals to 2 pi h bar over e3 minus e1 is equal to psi x t equals to 0. So this is your, so this 2 pi h bar over e3 minus e1, that is the minimum time after you will have this condition where, so that is what the minimum time was asked. So your minimum time is this. So I have like this part is clear.
Yes, sir.
Okay, so fine. Then
Sir, I have another doubt in first problem, sir.
first problem.
Yes, sir.
Okay, first problem. Yeah.
Sir, first step, sir, that sine 3 theta is equal to,
Right, right.
sir, the another step 3 a by 4 sine pi x by l. That in between step, I don't know, sir. Can you elaborate, sir?
Okay, so what I did, uh, so you mean this? How did I write sine cube pi x by L as two terms? No.
Yes, sir. Yes, sir. Yes, sir.
Okay, so yeah, so I have, like I basically used this relation. So this is the relation which I used. So like from this relation, you can see like I can write sine cube theta. From this relation, I'm writing as something. Uh, 3 by 4 sine theta minus 1 by 4 sine 3 theta. So can I write this one? Can I write this equation like from this relation? So this is your trigonometry identity.
Sir, I know the trigonometry identity, sir.
Yeah.
After that step, 3 by 4 sine theta will come. I don't know, sir.
3 by 4. So sorry. What happened?
Sir, the 3 sine theta, how come change it to 3 by 4 sine theta, sir?
So here on, you see here like you have 4 sine cube theta.
Okay, sir. Okay, sir.
So I'm dividing the factor 4 in both the sides of equation, or basically I'm taking the 4 to the other side. That is
Okay, sir.
basically
Okay, sir.
like,
Okay, sir. Thank you, sir. Thank you, sir.
so this is just identity. I have rewritten the identity and substituted in the wave function. So
Okay, sir.
nothing different or some other concept I'm putting.
Thank you, sir. Thank you, sir.
Yeah. So so this was the minimum time that was asked, and like, did we have something more here? Like, yeah, the uncertainty in the energy of the particle in the given state. So there is a bit of lag in my screen, which I am sharing it right now. So let me reshare my screen. So So okay, so that was the minimum time which we computed. Then further, we also have to compute uh, uncertainty in the energy. So how can you do that? Like so, just like so for the uncertainty relation, like as I told you before. Uh, so let me write what is uncertainty here. I mean what you have to compute. So this is what you have to compute. You have to compute square root of expectation of energy square and the expectation of energy, then square. So basically, like as I told you before, so expectation of energy is something you can write it as summation I, like lambda I c I mod square, the like magnitude of expansion coefficients. So that is what like I showed you at the beginning. So this is what, so how that was coming, like this is how, like I told you. So the same way you will follow, like you will also find, you can see a similar form of expression for this, that this will give you. So you follow through that those same step, you will get this, the this would be the form of expectation of E square. So like you will take Hamiltonian square, and that is uh, sandwiched between two uh, wave function psi. So was where psi is basically some linear superposition of eigenstates. So psi can be C1 phi 1 plus C2 phi 2, so till Cn finally. So yeah, so that is what like we need for the uncertainty in the energy. So like if you would see that we can calculate this like this way, delta E is basically or, so we have psi x. Let me. So we have psi x is like 1 by 2 phi 1 and plus by root I root 3 by 2 phi 3. So you just follow the same step again. So E will be uh, what is like 1 by 2 square, then eigenvalue of phi 1. So phi 1 is your ground state, so that is basically your pi square s bar square by 2m l square. Then plus you have uh, mod modulus square of I root 3 by 2. So you take I root 3 by 2 mod square. So then you have phi 3, I guess so. So phi 3 is corresponding eigenvalues 9 pi square h bar square by 2 9 square. So you got E here, and same way you calculate E square. So this won't be any different. Just there will be a square, and then you basically compute what is E square minus E square expectation minus E expectation school. So yeah, so from here, like I think you can just look to one step of algebra that will get your final result. So so this was for your question number two. So for your problem two. So I hope like did you able to guess this?
Yes, sir.
Okay, so if there is any problem with anyone, like they can let me know.
No, sir.
Okay, so fine, we can move on to the next. So now we have different quantum system. We have a linear harmonic oscillator. So this is the problem related to it. And so what is being asked here? So consider the normalized state sign of a particle in a linear harmonic oscillator. So whose state is given in this way. B1 is some coefficient again, and 0 denotes your ground state, and get 1 denotes your first excited state. So here you have to calculate what is the expectation value of the displacement x in the state side. So in this given state, you have to calculate the uh, average value of displacement of the harmonic oscillator. I mean, the particle which is undergoing harmonic oscillation, uh, basically your quantum particle. So, so again here, like, uh, uh, so you have your initial state B1 is 0 plus B1. Now, to calculate the expectation value of displacement, this is what you have to compute, just like how you would have computed for the expectation value of energy. And yeah, so to do this, you can you can substitute the exact form of uh, exact form of ground state and the exact form of uh, first excited state. Like I hope you know from your harmonic oscillator course that you might have done in the quantum mechanics one, where you have the wave function. So you have psi n x, some normalizing constant, some alpha n square, x square, and some Hermite function, like something of this form you have. So you can put the exact form of psi using that. Like here, like, let me write this. These are phi n. So these are the uh, eigenfunctions of your harmonic oscillator, just like how you had the eigenfunction for infinite well, which are basically square root 2 over L sine sine of n pi x over L. So same way you have eigenfunctions for harmonic oscillator, which is something would go like this form, which is pretty big form compared to the infinite well. So using these forms, like suppose if I want to substitute what is psi here, here it is b1. Uh, so ground state it will be basically phi 0 x, and you get phi 0 from here, and same way do you get phi 1 and put them, and that will be your psi. And so you, in order to calculate this complete this uh, inner product expression, you have to integrate it. So instead, like that would be a bit longer process to do. That would be a bit complicated way to reach to a result. But nonetheless, that is one of the important way to do that. Like how you will see how you find yourself, how elegantly you will see how these integrals will give you the uh, inner product result, and which would be basically same if you do by a different this using ladder operators. So, uh, so here you will see your X operator, the displacement operator, is expressed in terms of ladder operators. Again, you can go back to your harmonic oscillator course, like where you will see like how this uh, displacement operator can be expressed in terms of this A and A dagger. So what does this A does like? I mean this A dagger is basically your raising operator or creation operator. When it acts on the eigenstate of harmonic oscillator, it will raise the state. So I hope you people would be aware of this. And when you operate your lowering operator or basically that is an annihilation operator. So you have this. So so these are some basic information you need to have before computing this. So so here I can take the complex conjugate of psi, that will be B1 star, and yeah. So here in this question, nothing is said about the form of B1 and B2, so you can consider them as real. So let me write like this: B1 square, and so I have 0 x 0 plus f 0 x 1, then you have so here you will also have a rewrite again this sorry, so the first term you will have b1 square uh, bra 0 x get 0, and the second term you will have b1 multiplied with b2, then third term you will have again b1 b2 1 x 0, and the last term you will have b2 square uh, 1 x 1. So so this is what you will get. Like you will get four terms when you will compute this. So just like I took the complex conjugate of psi, that is basically b1 star, b2 star. So nothing is said about b1 and b2. This constant. So like you can treat them as some real. So b1 is basically equal to b1 star. So so yeah. So when you take this inner product, like you will get b1 square, and the this first term, the first overlap integral b1 b2, and so on. So so from here, like you can see, uh, you can put the form of x operator, that is this, which is given here right here. So uh, like if I would use b1 square h bar to m omega, or maybe I can, this h bar to m omega will appear in all the terms, so I can pull that out as a common factor, and uh, so I have b1 square 0 a plus a dagger plus b1 b2 0 a plus a dagger, then I have b1 b2 again, 1 a plus a dagger, then b2 square I have 1 a plus a dagger. So So right here you can see, uh, so the first term will give you like when a dagger acts on 0. So from here you will see, so from this relation, as I showed you right here, when a dagger acts on 0, that means it will give you 0 plus 1, 0 plus 1, that is 1. Same way when ax on 0, that is 0, 0. So, so on. If you do this, you will find like you will have the first, you will have b1 square. From first term, you will have 0 1. This is basically 0. From second term, you have b1 2. Uh, so here you will get 0 0. So here you will have 1, and again you have another b1 b2. The, the third term will also give you 0. So that is no, the third term will give you the contribution. So that is this, and the last term will again will go to 0. So yeah, so finally you will have, so finally you will have your expectation displacement operator will be twice of b1 b2 h bar over 2m omega. So uh, yeah, so like I hope like this is clear to, this is
Yes,
what
sir.
clear for you. Okay, so, so next like we had uh, so we had another problem on uh, ground state of harmonic oscillator. So I mean another problem on harmonic oscillator. So your the ground state is given as something psi of x a e alpha square x square, and alpha square is this quantity k over 2 h bar omega, where k is a Fox constant, and calculate the mean value of the potential energy. So the mean value of potential energy. So what is the potential basically for a harmonic oscillator? So which you are very much familiar, uh, half k x square. So this is your potential for harmonic oscillator, a linear harmonic oscillator. So and your yeah, wait, did my screen go off? Like, could you able to see my screen which I am sharing?
No, sir.
Oh, okay. So it went away. Sorry. So I'm sharing it. So yeah, I think you can able to see that one.
Yes, sir.
Okay. Thanks. Thanks. So yeah, yeah. I was telling you that like, so we have to compute the expectation value of the potential energy. The potential energy of your harmonic oscillator is half kx squared. So uh, yeah. So half k x square again, like the ground, the state which is given to you is this uh, psi of x a minus alpha square x square, and expectation of potential energy is basically you have to calculate this x square. So x square, how can you do this? Like, I mean, uh, you can you can, like, there are two ways to do it. Like, one way where you can compute this x square uh, is use the form which is given in the question. So x square is basically this thing you have to calculate, like 0 from uh, minus infinity to infinity dx psi star x square, uh, basically this x square psi star psi. So this is what you can do. So psi is given, psi star you can just take the complex conjugate. So which would be basically the same thing, right? That would be uh, something of this form. So dx x square a square e to the power uh, minus 2 alpha square x square. So you have to compute this integral. So this integral would be something some form of gamma function. So you can, I hope you can calculate this gamma function, and I mean you can compute this integral. So which would be in the form of gamma function. So but there is another way which just we discussed in the previous problem, where we already know the form of x, that is something h over 2m omega a plus a operator plus a integral operator. So you can do the same. So the state which is given to us, so we have been provided with ground state. So that means if we want to calculate x square, that is 0 x square x square 0, you basically have to calculate this. So again you can use the same idea what we just did in the previous problem. So you have a plus a dagger operator acting on this. So that is basically h over 2 m omega of a square plus a dagger plus a dagger a plus a dagger square. So like you will see, like you do the same technique which we just did in the previous problem, and from there you will find it, like you will get the expectation value of x square. So uh, so once you get the expectation form of x square, then your Vx will be half k times this thing. So that would be your expectation animation. So, so did you like get this part?
Yes, sir.
Okay. So if any doubts you can ask me. So we can move on to the next question if you people don't have any doubts. So yeah, so now we are being asked to calculate the wave function and boundary condition in the given two region of potential. So what is the potential given to us this time is this, like you have, so, so this is your space, the one dimensional space, and here you have potential like this, and uh, so at this is your x equals to 0. So for x greater than 0, you have a potential of v naught, and for x less than 0, you basically have zero potential. So, so, so you have uh, potential at uh, x greater than 0 and x less than 0. So you have two reasons, reason 1 and reason 2. So these are the two reasons where you have to determine the wave functions and also the boundary conditions. So you have only one boundary right here at x equals to 0. So at the boundary, what would happen to the wave function? What's the behavior of wave function? You have to also check them. So, so yeah. Um, so how can you do this, like and also it has been said that like you have to consider a case where the energy of particle, the energy of the one particle is less than this potential, and also uh, we have to consider another case where this energy of this particle will be greater than the potential. So, so what happens if you have a particle approaching from let's say from the negative x, from or like from left side of your screen, from this side, and if that quantum particle approaches this barrier, and when if it goes to the other side, if somehow like if it can go to the other side, then what would be the wave function in both region 1 and region 2? That is what you have to estimate, and also the boundary condition at x equals to 0, the barrier which you have to also check for that. Uh, so so let's say we have case E less than V naught. So this is your case one. So for E less than V naught, uh, let's say at reason reason one. So, so this is your case one. At reason one, uh, at reason one, your potential is zero. So if you have a potential zero, then what would be your form of wave function? So like to determine wave function, like how we do that, like we do it from Schrodinger equation. We solve the Schrodinger's differential equation, and from there we get the uh, we get some general form of wave function or our solution in the form of psi x. So like how do you do that basically? Like d square psi over dx square. So for one dimensional case, you have this form of Schrodinger equation, e minus u of x psi equals to 0. So you put just like how you have done for the infinite well potential also. So Same way you can do that. So we are at reason one. So at reason one you have wave function. Let's say psi one. You have psi two. So this is for psi one, and you have uh, energy less than v naught. So and but v naught in at reason one is zero. So basically you have d square psi one dx square plus 2 square square e psi one equals to 0. So, so if you go on and solve this differential equation, this is a very normal second order OD, second order ordinary differential equation. So you will get something psi 1 x as some constant, some you have like when you like do this when you try to solve this second order ordinary differential equation, you get two arbitrary constants. So one of them is I'm writing it as a. So a into so a multiplied with exponential of I k1x plus b. So b is your another uh, arbitrary constant for the differential equation which you will solve, minus I k1x. So e to the power I k1 plus or minus I k1 x is your general trial solution for this differential equation. So I hope like you must have seen from your mathematical course that I mean from your mathematical methods course you have solved many sorts of second order differential equation, and one of them is this. This is one of the simplest case where uh, you have a very straightforward uh, assumption of your trial solution as something exponential I k x to be your solution for the given second order differential equation, and and this k1 which I'm writing is basically square root of 2me over h bar. So that is your k1, and yeah. So and make sure this x only for less than 0 because we are at reason 1. So at reason 1 you will have this kind of uh, wave function. So and one more thing, like where you have to make sure like uh, psi 1 at x equals to minus infinity should be finite, because that is one of the important points of uh, wave function. Like for a regular acceptable wave function for a quantum particle at infinities, you should have your wave functions not diverging. They should be behaving in a regular way, or should be dying, should be like some you will see like in this case we have some finite value at infinity 7. So because we have uh, Euler functions, so these are basically oscillatory type functions. So yeah, and we know oscillatory type function whether it is trigonometry function like sine or cosine, so it won't like diverge at infinity. So so that is one point, and yeah, that is for reason one, and at reason two we can see at reason two we have potential v of x equal to v naught. So and we are at e less than v naught case. So that is what we will axiom. So at reason two we have Just writing the equation in this way. It's 2m h bar square uh, e minus e of x psi to 0. And here you will see, since e is less than p, so this term will be negative. The second term is negative, so I can write this way: minus 2m h bar square uh, on, or I can also write this way: uh, e minus v naught is 0. So, so when you solve this, uh, just wait a second. If this is your negative, so yeah, so this quantity is negative, so I have to write this way, or or else, yeah, or else, like, let me write psi 2 dx square minus of 2m h bar square uh, v naught minus c psi 2 0. So since it is negative, and when you solve this again, the second order differential equation, you will have psi 2x, some uh, arbitrary constant, this time let's say c, uh, e to the power k to x. So this time you will not have iota in front of k, because uh, now this will be, you will have solution something of decaying, or uh, exponentially decaying, or exponentially increasing. So then other arbitrary constant and minus k to x. So again, this is just solving the differential equation. Like, I hope you know how to do them. So that is just your, like, basic mathematical uh, technique to solve a second order ordinary differential equation. And yeah, and so, and again you have to take care of uh, boundary. So we are at region 2. So this x is for x greater than 0, and again you have to check side toward x going to infinity. uh, you have uh, you should get something, like earlier, as we found it, something finite was finite behavior was showing up at the negative infinity. So you would expect, like, we would expect the same thing at the positive infinity as well. So but you will see, like, when I put x equals to infinity, the first term will go away. So I mean, e to the power k 2x. uh, I mean, what I mean to say, basically infinity, since k to x go to infinity, then x goes to infinity. So that's why uh, we have to choose a C that will not make this solution infinite at when x goes to infinite. So the only way to like resolve this is to choose c equals to 0. So in that case, psi 2x will be only d of e minus k 2x. So that is your wave function and reason 1 and 2 for e less than v naught case. And now we can do the same exercise for e greater than v naught. So we have case 2 e greater than v naught. So so again at reason 1. So so yeah, again at reason 1 you have d psi 1 dx square. Let me. So at reason 1 you have u of x equals to 0. So that means again you have the same thing, d square psi 1 dx square plus 2m over x bar square. So here, like I forgot to mention here, K2 was 2m v naught minus e over h bar. And so here you have again e minus 0 psi 1 equals to 0. So this time if psi 1 equals to, this is basically the same thing which you had last time, k1x plus b k1x. So k1 is 2m e over h bar. So like, are you getting this? Like how this is like going through?
Yes, sir.
Okay. So if any problem, like you can tell right here. We can clarify.
Okay, sir.
Okay. So then at reason two, we again have we have v of x as v naught, and this time t sin square plus 2m h bar square e minus v naught psi 1 equals to 0. So this time this e minus v naught is positive. So if this is positive, then I can. So this is for side 2. Side 2, I will have c e I k 2 x plus d e minus I k 2 x. So now this time there is no exponential. It became an exponential increasing. Again we have e to the power iota because here because you have this quantity positive. Earlier when it was negative, uh, here in this part you had this kind of solutions. So now since we have taken positive, so here K2 will be 2m e minus v naught over h bar. So yeah, right. And again, like you can see you can check the asymptotic behavior. It will again uh, like it is again something behaving properly at x going to infinity. You have some finite value. So because again these are some oscillatory type functions, uh, and like at the boundary. So at boundary, what we want, like at psi one uh, x equals to 0 should be equal to psi 2 x equals to 0. So that is a boundary condition. Boundary condition. So we have missed to like calculate what is the boundary condition for the e less than v naught case. So we can go back there again. So here you will see in this case, like you can get uh, for just yeah, here let's say a plus b equal to c plus d. So just you have psi 1 x, you have psi 2 x, and at x equals to 0, this is what you get. And from the second boundary condition, from what is your second boundary condition? It is uh, basically d psi 1 x equals to 0 dx equals to d psi 2 dx x equals to 0. So again right here, like you will get you will take the derivatives. So and then at x equals to 0, you will find it what would be that. So the derivative first term will give you a I k1 e to the power I k1x, and at x equals to 0, that will be basically I k1a. So you get something like this: I k1 a minus b. Then this side we have I k2 c minus d. So that is your boundary condition how you compute it. So this is your boundary condition 1, and this is your boundary condition 2. So same way you can compute the boundary condition for the E less than V naught case, which we missed to do that. So yeah, so that is like how you write wave functions and boundary conditions. So we can move on to the next question if there is no doubt. So like was that the previous problem was all right? Like I mean, could you able to understand what was happening?
Yes, sir.
Okay. So basically, we're just writing the wave function at all the regions, depending upon what the potential is. You have to only solve the second order ordinary differential equation, and at boundary we have two conditions: the wave function should be continuous, and also the derivative of the wave function should be continuous. And to apply both those conditions, and you get two expressions, and those will be your boundary condition expression for your quantum system. So, so now, uh, so in this problem, like you have a wave function of a hydrogen atom, which is given by the following superposition of uh, energy eigenfunctions. So we know like for hydrogen atom system, a wave function is denoted by this, and since this is a like a three-dimensional quantum system, and you require like three quantum numbers to specify, and so you have n, l, m naught, three quantum numbers by which you specify your state of the hydrogen atom system. And so here what is being asked, like you have to calculate the ratio of expectation value of energy to the ground state energy. So I hope like you are aware that uh, energy eigenvalues for hydrogen atom system is something given by this. So uh, so for the ground state you have E1 E1 is a ground state, so that is given as minus 13.6 eV. And so what you have been asked here, you have to calculate the expectation and value of energy. So again, the expectation value of energy, you have a state something of this form: C1 51, C2 52, C3 53. So I can apply the same technique what we've been doing in the previous problems at the start of the session. Like we saw two of those similar problems, like how to calculate the expected value for energy. So do the same thing, like first term, like C1 is root 2 over 7, root 2 over root 7. So it's squared, I mean it's uh, mod square will be 2 over 7, and then you have psi 100. So psi 110, so psi 100, uh, its corresponding eigenvalue will be uh, minus 13.6 over 1 square. So that is basically your ground state.
Sir, sir, video is not working, sir.
Oh, um, again, okay. So how long like the video was not working? So
Sir, give start of the problem, sir.
okay, so could you see the screen right?
Yes, sir, Ripana.
Okay. So yeah, I was telling you like uh, the expectation energy of the uh, given wave function. I mean the state which is given for hydrogen atom system in this question is something of linear combination of its energy eigenstates. So just like the linear combination of energy eigenstates that we have been seeing. I mean in previous problems like which we did for infinite well and harmonic oscillator. The same way we have here for hydrogen atom system, where you have psi, which is a linear combination of three other eigenstates. So, so again, in order to calculate the expectation energy, you go through the same process. You take uh, you take the absolute square of this coefficients C1, C2, C3, and multiply respectively with their eigenvalues. So so here I'm using this same C square lambda. So I have 2 by 7 and psi and eigenvalue of psi 100. So eigenvalue for psi 100 is minus 13.6 over 1 square, and psi 210 is minus 13.6 2 square, because psi and eigen is minus 13.6 n square. So just I, I can go on doing that, like this is uh, E1 over 1 square plus 9 over 14, and I can write E2 as something like this: E1 over 2 square, and same way I can write 1 by 14 E1 over 3 square. Why I'm writing this way? Because I've been asked to calculate the ratio of expectation of energy with ground state. So that will give me 2 by 7 plus 9 by, so 2 square 14, and by 3 square 14. So yeah, so if you go on to calculate, you will get something. 2291 504. So this is just a like uh, similar person like what we've been doing before. So like quickly I can tell you what will be for eigen values for like now you have to compute this, and to compute that like you again need to know what is the eigenvalue for L square. So for L square like you have like L square when x on n and n, or basically your psi n and n gives you L times L plus 1 psi n and n. So with that like you can write again your eigenvalues. So your eigenvalues for psi and Lm will be L into L plus 1. So if you have psi 100, the 0 is lambda of psi uh, psi what is your second term, that is 210. So this will be uh, so there will be a factor of h bar square also. So h bar square. So here it will have 2h bar square. So yeah. So you will, if you do that, like you will get 2 by 7 multiplied with 0h bar square plus 9 by 14 2h bar square plus 1 by 14 6h bar square. So yeah, this is what would be the expectation value of L square and energy. So this is nothing new. Like we have just like done the exercise again. Uh, just like how we have done, how we have computed expectation value of energy like earlier in other potentials. It's the same thing. So now like yeah. So like did you get this part? Like that was the last we had.
Yes, sir.
Okay. So okay then. So good. Like we can probably end our tutorial session right here. So
Sir, can
uh,
we have PDF, sir?
sorry.
PDF, sir. PDF
Oh
file.
yeah, yeah, yeah. Like I think this PDF and the recording session will be shared with you. Like I think you can access it right. Like maybe through your NPTEL email, or maybe you can go to your NPTEL portal and there you can get. So you can get all the materials that we have discussed right here
Okay,
today
sir.
this evening. So that will be shared to you like very soon. So.
Thank you, sir.
If there's any more doubt, like you can ask, like related to the course or something which was not clear in this problem solving session, or something more like you have to like you have from your side, like you want to add something, some comment, like you
Sir,
can. Yeah.
sir, any standard books for this, sir?
For this, like today, what we discussed, like some standard, like, there are many of them. Like you can all, of course, start with a basic one which everyone loves. That is David Griffiths, and
Okay, sir.
or like you can also go with one similar version of it. Like I mean, that is Jet Li's,
Okay, sir.
or you can go for advanced topics. You can go for this like Sakurai, and so
Sakurai, sir.
yeah, yeah. For
Okay, sir.
if you want some more advanced problems and some more advanced topics you are not very clear, like you can go there.
Okay, sir. Thank you, sir.
If there's anything more you want to say, like
No, sir. No, sir.
okay, so then fine, it's good. We can end it right here. So also like uh, okay, there is a question from someone like certificate where will sorry. Uh, where will our exam? Okay, again that also like will be clear to you. So there will be a different examination centers. Like you will pick a examination center nearer to your place, and you can go and give your tests there. So like it will be communicated with you like well before uh, when your uh, test or exams will be declared. So there will be enough time to like uh, to let you know exactly where you would be there for your exams. And yeah, I think that will be communicated well through email. So right now, I do not have any information regarding that. So is anything more?
No, sir.
Okay, so okay, good. We can end it right here. So see you. So bye.